Afternoon, students. Welcome to the, I think it is the last lecture on the theory portion under module 3, because we have covered rolling, we have covered forging, extrusion. Okay, so these were the major topics under module 3, and now we have smallest topic, very small topic, that is bar and bar drawing. Okay, so wire and bar drawing we are going to cover today. Okay, so if you remember your extrusion processes, there was a reduction in cross-sectional area. Okay, so in under extrusion processes, what was being done? Your metal block was being forced to pass through a die. But in the case of drawing, the process may look similar to looks like similar to your extrusion process, but it is quite different as far as the forming mechanism is concerned. Okay, so under drawing, what we are doing, drawing is an operation in which the cross section of a bar, rod, or wire is reduced by pulling it through a die opening. Okay, so here what we are doing, we have this die and we have this work billet or your initial workpiece, which is being pulled from this end. Okay, from right hand side, this is being pulled. But what was happening in the case of extrusion, this your initial work billet was being pushed inside your die, and due to compressive forces, this your work piece was getting deformed, or the cross section area was changing because of squeezing of your work metal. Okay, so under drawing, what we are doing, suppose we are pulling this end, and if we pull this end, there will be some tensile force will be generated at in this portion. Okay, and due to this tensile force, what will happen, it will try to pull the work billet which is in the left hand side of your die. Okay, and as soon as this is being pulled, what will happen, this area or this zone will be under compressive forces. Okay, so in drawing, it is noticeable that both kind of stresses are developed, tensile stress as well as stresses are generated in the case of drawing process. Okay, so the major difference between the drawing and extrusion is the work is pulled through the die in drawing, whereas in the case of extrusion, it is pushed through the die. Okay, so in the case of wire and bar drawing, the terms are the bar drawing is basically used in the case of when the diameter of rod or bar is high. Okay, large, for large diameters, the term bar is used, and for smaller diameter varying from 2 mm or less than 2 mm, 1.5 mm, and which may be up to 0.03 mm. Okay, so the dimensions or diameter of this dimensions, they are termed as wire. Okay, so the process which is used to reduce the diameter, small diameters, okay, of less than 2 mm, it is termed as wire drawing. Okay, so under wire drawing, what we are doing, under drawing, what we are doing, we have two stress components that are present. One is tensile. Tensile stress is generated due to the pulling action, that we are pulling your workpiece or your wire through a die opening. Okay, and compressive stresses are generated because the metal is squeezed down at its passes through the die opening. Okay, so from the one side of your die, there are compressive stresses, and on the another side there are tensile stresses. And basically, these compressive stresses are being generated because of tensile stresses, because we are applying force on the one end of your wire, that is, if we are pulling this wire, and subsequently tensile stresses are generated in this bar. Okay, and because of this pulling action, there this whole work piece is being drawn towards right, and because this diameter is higher, so there is a squeezing of your work metal or your wire between the surfaces of die. Okay, so here in this portion, the compressive stresses are generated. Okay, so this is how this process is different from your extrusion processes, where only compressive stresses were generated in the case of extrusion, but in the case of drawing, both the type of stresses are generated, that is tensile stresses and compressive stresses. Okay, so there are few terms that may be analogous to your extrusion process, so that's why I will move a little bit faster. Okay, so change in size or reduction in area, it is given by the term R equal to change in area upon original area. Okay, so change be given as AO minus AF upon AO, where AO is your initial area of your wire, and AF is your final area. Okay. Similarly, the change in diameter may be termed as draft, and this difference is given as small d equal to DO minus DF. Okay, so this change in original change in diameter of your bar or wire is termed as draft, and it is given as D equal to DO minus DF. Okay, now we have to understand the mechanism, underlying mechanism. What are the force requirement? What are the stresses generated in the case of your drawing process? Okay, so whether it is bar or wire, the mechanism is almost same. Okay, so first we will consider the case when there is no friction between the surfaces of your die and your workpiece, okay, or your wire or bar. Okay, so in that case, true strain may be given as epsilon equal to natural log of AO upon AF. Okay, so here if you see, this term can be mathematically AO upon AF is equal to 1 upon 1 minus R. Okay, so here R is your reduction in area. Okay, if you remember the value of R is R equal to AO minus AF upon AO. So if you put this value here, then it will come to AO upon AF. Okay, so here we can see that the true strain is epsilon equal to natural log of AO upon AF, which is again equal to natural log of 1 upon 1 minus R. Okay, and similarly, stress may be given as sigma equal to average flow stress Y bar F multiplied by true strain. Okay, so Y bar F multiplied by epsilon, which here if we put the value of epsilon, it will become Y bar F natural log of AO upon AF, where YF bar, it is well known. In previous lectures we have covered that average flow stress is given as K epsilon n upon 1 plus n. Okay, and now we will come to the uh, mechanics of drawing, considering the frictional values. Okay, I can see there is some lagging in Y voice and PPT changing. Okay, so I will sometimes slow down Y voice in order to match the slide changing frequency, because I am seeing in mobile the slides are changing a bit late. Okay, so here in the case of when the friction is considered, the flow this stress may be given as sigma d equal to YF phi 1 plus mu tan alpha natural log of AO upon AF. Okay, so these are the formulas which has been developed by different researchers. I went through multiple books, but I was not able to find the exact derivation of these formulas. Okay, so we will remember these formulas, and if required, we can go through research paper which are available. Maybe the explanation of these formulas may be available in few research paper, those by the authors, those who have developed these formulas. Okay, so for
Sir,
now,
sir,
yes.
it is given in one of the NPTEL lectures.
Uh, it is
Given in one of the NPTEL lectures available on the web. The proof of that formula, sir.
okay. So derivations are given there. Okay, so I cannot hear. Somebody was saying, but okay. So then this phi is your phi is a factor uh, that is basically taken into consideration because of inhomogeneous deformation, and which is given as phi equal to 0.88 plus 0.12 uh, d by lc. Okay, where d is your average diameter of work during drawing, lc is your contact length of work with the draw die, and here you can calculate average diameter as d equal to do upon df, and contact length may be calculated as lc equal to do minus df upon 2 sin alpha. Okay, so accordingly we can calculate the force. We have value of sigma d from this equation. Okay, then af we already know. So the forming force or the drawing force may be calculated as F equal to AF into sigma D. Okay, so uh, these were the few numerical formulas which are important when we consider the drawing processes. Okay, now we will move further. Uh, that is the what is the maximum reduction uh, per pass which is possible in the case of drawing processes. Okay, so the first question is why entire reduction is not possible in one pass. Okay, so why it is not possible? There is some reason. Okay, why we cannot get entire reduction in one pass? Because as we increase reduction, the draw stress increases. Okay, so as this draw stress increases with the increase in reduction, what will happen? This draw stress will increase slowly and will become more than the yield strength of your metal. Okay, or your wire. Okay, wire or bar. Okay, if this draw stress has exceeded the yield strength, what will happen? Material will not be extruded from your die, and what will happen? It will simply elongate and break after certain time. Okay, so when this draw stress has exceeded the yield strength, what happens? The drawn Y will simply elongate instead of new material being squeezed through the die opening. Okay, so no further material will be squeezed through the die. Okay, and for the successful drawing, what is required? The maximum draw stress must be less than the yield strength of your existing metal. Okay, so we have to choose the maximum reduction or the reduction ratio in such a way that uh, the draw stress should not exceed the yield strength of your metal. Okay, so there are certain empirical formulas related to your maximum reduction per pass, that which is possible per pass, and it is given as the maximum possible per pass you can find out using some empirical relation, which are as follows. In the case of in order to achieve the maximum reduction, consider the perfectly plastic material. Okay, it means the n equal to 0, and hence the average flow stress will become maximum flow stress, that is equal to y. Okay, so this y bar f, this sigma d will be equal to y bar f natural log of a upon af. Okay, since y bar f is equal to y, and this will be equal to y natural log of AO upon AF, AO upon AF. Okay, so this natural log of AO upon AF is equal to natural log of 1 upon 1 minus R. Here R is your reduction ratio. Okay, so this term we know already that for the maximum reduction, possible reduction, yd is equal to y. Okay, so this whole term will be equal to y. Okay, so y will be cancelled, and therefore natural log of 1 upon 1 minus r will be equal to 1, which is explained under the point number 2. Okay, so here we can see that AO upon AF equal to 1 upon 1 minus R. This must be equal to E, because if you see natural log of 1 upon 1 minus R equal to E. Okay, so if we see 1 upon 1 minus R will be equal to E. Okay, so we already know the value of E is equal to 2.718 3. Okay, so this is the maximum value. Okay, so f the so so the maximum possible area reduction will be a0 upon af, which is equal to E. We have calculated from here AO upon af equal to E, or 1 upon 1 minus r equal to E. And we already know the value of E from mathematics, that E equal to 2.7183. Okay, so similarly, by putting the value of E in this formula 1 upon 1 minus r equal to E, we can calculate the maximum possible reduction Rx, and which comes equal to Rx equal to E minus 1 upon E, which is equal to 0.632. Okay, so the maximum possible reduction in the case of drawing is 0.632. Okay, and the maximum possible area ratio is A upon AF. Okay, so now we will move further related to drawing. Okay, so drawing is generally performed at cold working. It is a cold working process. It is normally performed at room temperature. Okay, and it is generally used to produce round cross section. But other shapes like extrusion process, there were multiple type of shapes that could be extruded using your extrusion processes. The same, some other shapes may be drawn using your drawing process. Okay, so there are various kind of products that can be extruded using your drawing process. These products are electrical wire, cables, wire stock, okay, coat hangers, and shopping carts, etc. These are the products that can be produced using your drawing process. Okay, then we have rod stock to produce nail, screws, rivets, springs, and other hardware items. These also can be produced using your drawing process. Okay, bar drawing is used to produce metal bars for machining, forging, and other operations. Okay, so these were the various products that can be produced using your drawing process. Okay, so there are certain advantages, obviously, of your drawing process. The advantages are the accurate dimensional accuracy or close dimensional control is possible in the case of your drawing process. Good surface finish is produced. The surface finish is very high in the case of product which are produced using your drawing process. Okay. There are improved mechanical properties such as strength and hardness, and the drawing process can be easily used for mass production. Okay, so these were the major advantages of drawing process. Now we will come to the drawing equipments which are used in the drawing. Okay, so first we will take equipment in the case of bar drawing. So here in the bar drawing, we have draw bench. Okay, this is your draw bench, which is consisting of your entry table, die stand, carriage, and a exit rack. Okay, so the major component of draw bench are entry table, die stand, carriage, and exit rack. Okay, so in here the carriage is used to pull the stock through the draw die, and it is driven by the hydraulic cylinder or motor driven chain. Okay, so you can see there is a draw bench on which you can find die stand, carriage is there. Okay, drawn bar are you can see here. Okay, so this is your starting work, and this is your exit point or exit of your drawn wire. Okay, so this way this bar drawing is done. Okay, then we come to the drawing equipment which are used in the case of wire drawing. Okay, in the case of wire drawing, we have multiple machines. Okay, so in the case of wire drawing, it is done on continuous drawing machine that consists of multiple draw dies separated by accumulating drums between the dies. Okay, so here what we have multiple dies, and with these dies are separated by accumulating drums. Okay, which are kept between these die. Okay, each drum is called as a capstan and is motor driven to provide the proper pull force to draw the wire stock through the upstream die. Okay, so these drums are some motion is given to these drums by some mechanical forces or by the motor, so that they are able to provide full force to draw the wire stock. Okay, so it also maintains a modest tension on the wire as it proceeds to the next draw in the draw die in the series. Okay, each die provide a certain amount of reduction in the wire so that the desired total reduction is achieved by the series. Okay, so since there are multiple die and there is reduction at each stage. Okay, at each die certain amount of reduction is provided. Okay, in the case of wire. Okay, so here you can see the some arrangement of wire drawing process. Here you can see it is your initial starting block, and it is being folded on a capstan drum, or which can be termed as capstan drum, or hold multiple loops of wire. Okay, so here multiple loops of wire are done on your this capstan drum, and after that it passes through a die. Okay, then we have another this through this die there is certain amount of reduction in your wire, and after that what is happening, there is another capstan drum. Okay, on which there is again some loops, multiple loops of wire. Okay, and this capstan drum is being driven by a mechanical motor. Okay, it is being being rotated by a motor, and again the wire is passing through a second set of die. Okay, and after passing it through a second set of die, it is being again looped on a third capacitance drum, and it is coming out as your final product. Okay, so this is how the equipments in the case of drawing are placed. Okay, so this is a continuous drawing of wire. This is a process in which there are multiple dies that have been kept in between capacitance drums. Okay, so this is how the reduction in wire is taking place. Okay, now we will try to understand these drawing dies, these, because these drawing dies are the important, which are basically responsible for the reduction of your diameter of bar or wire. Okay, so we will try to understand what are the major regions inside your drawing dies. Okay, so these major regions are, there are four types of major region. In some books it is given as five, but for the you can say for the deformation geometry, or from the study point of view, there are four major regions in the die. First one is your entry region, which is usually a bell-shaped mouth that does not contact the work. Okay, you might have seen the bells inside the when you visit any temple. There are large shaped bell shape you might have seen. So your entry region exactly looks like the shape of your bell, which you might have seen in temples. Okay, so it is this is the entry region. First region is the entry region, which is usually a bell shaped mouth that does not contact the work. Okay, and its purpose is to funnel the lubricant into the die and prevent scoring of the work and die surfaces. Okay, then we have second region, another region, that is the die approach region. It is the region where drawing process occurs. Okay, so here the actual contact between the die and your wire happens in the case of approach zone. Okay, so this is the actual zone where deformation is taking place. Okay, so under approach region, what is done, it is a cone shape with an angle, half angle, normally ranging from 6 to 20 degree. Okay, this degree has been mistyped. Okay, this is 6 to 20 degree, this angle. Okay, then we have third important region, that is called bearing surface or land. Okay, so this bearing surface is the you can say important dimensions or important region which determines the final size of your wire or bar. Okay, so normally this bearing surface is straight. Okay, I will show in the next diagram so that for better clarity. Okay, and after the completion of this bearing surface, we have exit zone. Okay, under this exit zone, uh, you know, it may be also termed as back relief, and it is provided with a back relief angle of up to 30 degree. Okay, so here you can see your complete die, where you can easily understand the different zone in the die. Okay, so here you can see this is your entry region, initial entry region. You can see this is your entry region. Then we have approach angle, this approach region from this point to this point. Okay, this is your approach region, and this angle is called as approach angle. Okay, so this approach angle is generally kept from 6 degree to 20 degree. Now we have this portion, that is the third region, which is called as bearing surface or bearing length. Okay, so here you can see the important dimensions that is responsible for the final reduction in the wire is your bearing surface. Okay, so this is how your bearing surface determines the dimensions of your final product. Then we have back relief angle. This is your back relief region, and this angle is generally kept as 30°. Okay, these are the important terms related to drawing dies, which are important from the point of study. Okay, now I will come to the last point in the drawing, that is preparation of work in the case of drawing. Okay, so how your work or initial block is, what preparation is needed on your bar or wire drawing wire to draw it through a drawing die. Okay, so these are the three important things which are important, that is the annealing, cleaning, and pointing. Okay, so why this annealing is done? Annealing, I think you might have studied in material science course, that annealing is done to increase the ductility of any given metal. Okay, so because since we have to reduce the diameter and we have to draw your wire or bar through a die opening by pulling it. Okay, so obviously it should have sufficient ductility so that it can be drawn through die. Okay, so first step is annealing. Annealing is done to increase the ductility of your workpiece. Then we have second step, that is the cleaning. Okay, so cleaning is required to prevent the damage of work surface and draw die. Then we have third point, that is the pointing, which involves the reduction in the diameter of starting end of the stock so that it can be inserted through the draw die to start the process. Okay, this is usually accomplished by swagging, rolling, or turning. Okay, so this pointing is nothing but because we have to start your drawing process, so we have to make a pointing surface at the starting of your bar or wire. Okay, so these are the three important things or three steps that are done for starting your drawing process.